Okay, so let's have a look here. We've got our sample proportion, populations, okay. So we're told we're within 2 standard deviations exactly. So I know we've spoken about our sample and we've got our 1.96, but we're told here we're 2 standard deviations. So what we do know is that some p hat minus 2 times the standard deviation, p hat plus 2 times the standard deviation gives me 7 to 9, yeah? So clearly our p hat value is going to be halfway between those 2 points. So 7 plus 0.7 plus 0.9 over 2 is equal to 0.8. So our p hat is 0.8. So that means from here we've got, if you like, 0.8 minus 2 times the standard deviation, or 0.8 plus 2 times the standard deviation, okay? So you could use either one of these to come up to solve the equation. So if I go with 0.8 minus 2 times, well, what is the standard deviation? P hat 1 minus P hat over N. That has to equal 0.7, all right? So let's take the 0.7 across, other one over. So that means I'm going to end up with 0.1 is equal to 2 times square root of 0.8 times 0.2 over n. 0.05 equals the square root of 0.16 on n. So what's that going to give me? So if I square both sides, I'll get 5 on 100 squared is equal to 0.16 over n. So n is equal to 16 over 100, all divided by 25 over 1,000. So flip it upside down and multiply. 16 times 16 over 100 times 1,000 over 25. Get rid of a few zeros. 160 on 25 equals, not too sure if that looks right there, boys, but I reckon 100 squares should be 4 zeros. 4 zeros, make that 1,600, leaves me with 64. Okay, so that kind of makes sense. I thought there was a problem there because 160 on 25 is not going to give me a whole number. So that doesn't make sense because n is our number of trials. So 64 looks a bit better. All right, what's our next question about? Random sample of n undergraduate universities were asked whether they were going to complete a second degree. 60% said no. So P hat really, because it's a sample, isn't it? Is equal to 0.6. Well, there we go. So P hat is equal to 0.6. There's a nice start. What's the next part? P was? Okay. Write an expression for E, the margin of error for this estimate at a 95% confidence interval. Okay. So we know our margin of error. Well, margin of error is equal to, for 95% confidence, 1.96 times the square root of P times 1 minus P hat on N, which is equal to 1.96 times the square root of, what did we say, 0.6? 0.6 times 0.4 over N, which equals 1.96 times the square root of 0.24 on N. In terms of N, okay, so we can't do much more with that. I guess we don't often like decimals in fractions, so maybe we should put 1.96 times the square root of 24 over 100n, okay, because there's my 0.24n. If the number of people in the sample were halved, what would be the effect on the error? So that simply means that n is equal to a half n, if you like. So let's compare what the new error would be. So 1.96 square root. What if we simplify? Let's write that as, let's just simplify the fraction. Write it as times the square root of 24 over the square root of 100 times n, which in this case is a half n. So equal to 1.96 times the square root of 24 over the square root of 50 times the square root of n, which is 1.96 times the square root of 24 over root 50. What's that? 5 root 2 times root n. Oops, root n. So what if we compare the original error and we'll divide them and just work out what sort of a change that is. So my new error is root 24 over 5 root 2 times root n. And if I consider my original error, let's tidy that up a bit. Obviously it's 1.96 times. 1.96 times root 24 over, well, the square root of 100 is 10 root n. So what sort of a ratio does that give me? So let's flip the bottom one upside down and multiply. 10 root n over 1.96 times root 24. So let's go 196 crosses 196. Root n will cross with root n. Root 24 with root 24. That gives me 10 on top of 5 on root 2, which is 2 on root 2, 2 root 2 on 2, which is root 2. So therefore my error, in fact, is root 2 times bigger. Okay? Okay, so what have we got here? We know from in here, so for 2 marks here, I need to say something about the distribution. So certainly binomial distribution because it's independent. We have 20 trials, probability of success is 5/8. Okay, so the probability that x is greater than 10, probability x is greater than or equal to 10 is equal to binomial CDF 20, 5/8, 10 to 20, and that's going to be equal to 0.91, how many decimals? 4, 0.9153. Okay, the next one's conditional. So the probability that x is greater than or equal to 15 and x is greater than or equal to 10 over the probability that x is greater than or equal to 10. So what numbers are greater than 15 and greater than 10? Well, that's simply the probability that x is greater than or equal to 15 over probability that x is greater than or equal to 10, which is greater than 15.178765 over 0.91529, which to 4 decimal places gives me 0.1953. So we now got a sample size here. What's happened there? Got a sample size. So the expected value is simply equal to the proportion equal to the population proportion, which is equal to 5/8. And my standard deviation, so the standard deviation is equal to the square root of 5/8 times 1 minus 5/8 over the sample size, which was 20. Now, given my variance is the standard deviation squared, I can get away with, if we put it therefore, the variance of p hat is given by 15 on 64 divided by 20, which is 15 over God knows what that is. Let's make that a 3. Over 1280, which is equal to 3 on 256. Obviously, we've got a calculator, so make use of it. So that's my variance, remember. So when we have to get onto our standard deviation, we'll get a square root of that. So find the probability that a sample proportion lies within 2 standard deviations of 5/8. Give your answer correct to 3 decimal places. So let's first of all work out 2 standard deviations. So 2 standard deviations will be 5/8 plus or minus 2 times the square root of 3 on 256. So on my CAS, that'll give me 5/8 plus or minus. Probably can't do a real lot with that. So let's just go straight to the calculator, and that will give me the interval of 0.408842. Okay, so we're looking to get the population, the sample proportion within those areas. So since we have a sample size of 20, well, what's 0.408 of 20 times 20 and 0.842 times 20 gives me 8.17 and 16.82. So we're saying it's got to be between those two values. So means that the number of observations are going to have to be greater than, well, it can't be 8 because it's got to be greater than 8.17. So I've got to go greater than 9 and less than 16. So I'm looking for that. Okay, so remember we're binomially distributed. So binomial CDF with my 5/8 20, 9 to 16 will give me 0.939. All right, so there's a little bit in that one. So we've got a conditional one here. So what have we got? We're going to have, we need the probability that p hat is greater than 3/4 and p hat is greater than 5/8 over the probability that p hat is greater than 5/8. So my top line has got to be bigger than 3/4 and bigger than 5/8. Well, 3/4 is 6/8. So it's the probability p hat is greater than 3/4 over the probability that p hat is greater than 5/8. So then given that we've got a binomial distribution, if I multiply both by 20, 3/4 of 20, probability that x is greater than or equal to 15 over, what's 5/8 of 20? Probability that x is greater than or equal to 12.5. Now, obviously, we can't have a 12.5 in a binomial, so we're going to have to work with probability that x is greater than or equal to 15 over the probability that x is greater than or equal to 13. So using my CAS on that, 0.1788 over 0.5079 is equal to 0.352. So I guess just to make sure those numbers there, 0.1788 over 0.5079. Okay, so we've got to have those conditional rules sort of organised and structured in our heads or in our notes. All right, Paula is a member of Fully Fit's Gym in San Francisco. She completes tests every month as required, but otherwise does not attend regularly. So her fitness level varies over many months. Paula finds that if she's fit 1 month, the probability that he's fit the next month is 3/4. And if she is not fit 1 month, the probability that she is not fit the next month is 1/2. Okay, if Paula is not fit one particular month, I reckon let's do a bit of a tree diagram. We'll call it fit and not fit, fit, not fit, fit, not fit. If she is not fit in one particular month, what is the probability that she's fit exactly 2 of the next 3 months? Okay, now straight away, because her fitness levels and the likelihood of her being fit varies, okay, so it changes from month to month. It's not a binomial, all right? So let's instead think about where are we at. So she's not fit at the start. We've been told not fit. Okay, which means then if she's not fit, the probability of her being fit in this spot here, let's see, probability that she is not fit the next month. If she is not fit 1 month, the probability that she's not fit the next month is 1/2. So not fit into not fit is 1/2. So there's got to be 1/2 as well. So not fit into not fit, that's 1/2 as well. But if she's fit, the probability that she's fit again is 3/4. Okay, so that's our little structure. So if Paula is not fit in one particular month, so let's think about what the options. She's not fit here. What is the probability that she is fit in exactly 2 of the next 3 months? So we've got 3 more months to work with, haven't we? So it's either fit, fit, non-fit, fit, non-fit, fit, fit, or not fit, fit, fit. So they're the ways that she can be fit in 2 of the 3 months. So what's that in terms of probabilities? So we're starting at not fit. So not fit to fit is 1/2. Into a fit again is 3/4. But then from fit to a not fit is 1/4. Next one, we're starting at not fit, going into fit. So not fit into fit is 1/2. But then I'm going to go from fit to not fit, which is 1/4. And then I'm going to go from not fit to fit, which is 1/2 again. And we're going to start with not fit into not fit for the final one, which is 1/2. And then not fit into fit, which is 1/2. And then fit into fit, which is 3/4. Yeah? So what's that going to give me? What's that? 16 on 32. So we've got 3 on 32 plus, what's that? 8, 16. 1 on 16 plus 2 2s are 4, 16. 3 on 16. So let's make everything 32s. So that's equal to 3 plus 2, which is 5, plus 6, which is 11 on 32. So when Fully Fit surveyed all the throughout the world has found that the time taken by members to complete another exercise routine T is a continuous random variable. Okay, so continuous, we know straight away we've got some integration that we need to do. And the probability function is defined below. So there's our rule for us. Find the expected value of W correct to 4 decimal places. So what do we know here? I know that the expected value of W is equal to the integral of x times P of x dx. So we've got two distinct intervals, so we go two distinct integrations to do. So my expected value, room out here, is going to be equal to the integral between 1 and 3 of W minus 3 squared plus 64 on 256 times W dW plus the expected value of the integral between 3 and 5 of W plus 29 on 128 times W dW. Okay, so straight away I'll go straight to my CAS and discover that if I add both those values together, I get 3.04. How many decimal places? 4 decimal places. 3.0458. All right. What's the next part? The next part says, in a random sample of 200 fully fit members, how many members would be expected to take more than 4 minutes to complete their task? Right, so the probability of taking 4 minutes. So what is the probability of taking 4 minutes? So probability of, oops. So the probability that W is greater than or equal to 4, well, if we go to the bottom integral, we know that from 4 means 4 to 5 of W plus 29 on 128 dW. And so if I work that out, I get 67 over 256. So that's the probability that someone will take. Therefore, my expected number is going to be 200 times 67 on 256, which is to the nearest integer. So it's 52.34 people, which is equal to 52 people. Okay.